Well, good afternoon to some, good morning to others, but welcome to everyone. My name is Steve Light, and I'm with Common Ground Alliance, and we welcome you to our Technology Spotlight webinar. CGA's Technology Committee is beginning a series of webinars. These webinars seek to educate and highlight a technology that is advancing damage prevention. This is the very first webinar we've done, so we're all making history here. We're thrilled that you're taking time out of your busy days to be with us. As you've noticed, if you want to go to the next slide, please, you've noticed we're using Zoom. And of course, this webinar is being recorded, so it'll be posted after the meeting, after the webinar on our technology hub. And I'll have some information for you later on how you can access that, or you can share a link to that for folks who may have missed this. But since we're using Zoom, just wanted to quickly show folks that there are settings that you'll want to check out. Be sure to pay attention to the audio settings that you'll see there on a toolbar that should be across the top of your screen. We also have the chat and Q&A features, which will allow you to type in questions. Those are questions that will either be apparent for all of the participants, or you can message just the panelists themselves. We will have time for questions and answers at the end of the webinar, so certainly get your questions in at any point that you feel comfortable. I'm happy to be joined on our venture today by Nick Starkey and Matt Briggs. Next slide, please. Thank you. They are representing our technology committee. Nick is currently one of the co-chairs of the committee, and then Matt is task team chair who is working on the webinar specifically. Nick, welcome, and thanks for being with us today.
Yeah, thanks, Steve. I appreciate it. If you want to just click over one more slide for me. I just wanted to say thank you to everybody that's taken the time to attend the webinar. With our technology committee, we got a couple things that we do. We have an annual report that we publish that you know of. And our main goal is to try to be a vessel of communication in regards to technology that helps the damage prevention industry, and hopefully with enough information be able to help drive that focus. So our webinars that we're trying to do 3 times a year, this is one of them. This will be the last one, and we'll be looking for another one in the first quarter of next year. And I have the pleasure of Matt Briggs, who's a part of our team now, helping facilitate these webinars. And I'll go ahead and I'll pass it off to you, Matt.
Much, Nick, and first and foremost, hello everyone, and thank you for sharing your morning or afternoon with us today. For some, like Nick had said, my name is Matt Briggs, and I'm a sub-chair with the CGA Technology Committee, heading the webinar series today. So we're excited for the opportunity to speak to you folks today. We have a fantastic presentation for you all, and a very intriguing technology that has really the potential to be pretty revolutionary, I think, in this space. Dr. Paul Dickinson leads FOSA, the Fiber Optic Sensing Association, and him and his colleagues will speak comprehensively about the technology today and highlight specific case studies that further support the real-world applications. I'll pass it to Paul here in a moment for introductions to him and his colleagues, but first, again, if any questions arise throughout the webinar today, please type those in the chat as previously mentioned by Sarah. With that, Paul, take it away, please, sir.
So thanks, Matt, and thanks to everyone who's helped organize this. We're super excited to be here today with the CGA member community. So good morning, good afternoon, wherever you happen to be. We appreciate the invitation by the Technology Committee. We're very excited for the discussion. I'm Paul Dickinson. I'm the Director of Technology Partnerships for Duraline and the Vice Chairman this year of the Fiber Optic Sensing Association. I'm joined today by 4 esteemed FOSA member company colleagues who later in the presentation will introduce themselves and be presenting real-world use cases for utility damage protection and monitoring. Since we began this, let's see, maybe 6 months ago, interaction with CGA, we discussed the potential the fiber optic sensing technology might have in helping to reduce the significant level of infrastructure damage and life safety events that occur annually in the US. That $60 billion indirect and direct damage figure always sticks it with me as something that we want to together try to mitigate. So today we're going to briefly describe the technology, how it might be integrated into the CGA member toolkit for damage prevention, and then we're going to mention applications that are actually already occurring for pipelines, electric utilities, and telecom. Next slide, please. So first of all, I want to start off by introducing what FOSA is. The Fiber Optic Sensing Organization is a nonprofit industry association formed in 2017 in Washington, D.C. So we're actually celebrating our 5th anniversary this year. We're super excited about it. We promote the use of distributed fiber optic sensing across many markets. You see a snapshot. My slide did not change. Did we change the slide? Ah, there we go. Thank you. You see a snapshot of many applications where this technology is currently used for monitoring of infrastructure and key assets. Many markets are just simply not aware of this technology. That's why we're excited to be here today. So we bring awareness and education of the benefits of DFOS technology through multiple ways. Technology awareness campaigns, advancing public policy through engagement with U.S. legislators, and also outreach to commercial organizations and organizations like this. The membership is open to companies globally who make, install, support, and use, such as you, these distributed or quasi-distributed fiber optic sensors. We like to encourage hands-on activities. The members organize, they manage, they collaborate amongst themselves, and we do that through committees such as the Technology Committee, Smart Cities, Outreach Committee, and Public Policy. Next slide, please. So first of all, we need to describe what distributed fiber optic sensing is. The first point to note is the word distributed. The sensing takes place continuously along the length of optical fiber, the entire length, as compared to a discrete sensor or an IoT type device, which would monitor from a single location. The monitoring is done using fiber optic cables, where just a single strand of optical fiber is used as a passive sensor. It requires no power along the fiber itself. So the illustration at the bottom is useful in that there's hardware and software appropriately located centrally in a rack, similar to how you locate telecom equipment, and the signal is sent along the fiber. So for the entire length of the fiber cable, there's 24/7 continuous monitoring with resolution as precise as several feet or meters, and the measurement of temperature, strain, and acoustic energy is possible. So whether it's temperature, strain, or acoustic energy, each of these has unique applications for infrastructure, and several can actually be combined on a single system. But that's a longer talk for another day. So for the purposes today and the mission of reducing infrastructure damage, we'll be focusing on distributed acoustic sensing, or DAS, which is the acronym. Next slide, please. So let's talk just a little bit more about the technology. So I want you to think about this in your mind's eye. Envision a fiber optic cable that's running down your utility right away, typically buried in conduit, either right next to your gas line, your water line, your electric cable, or your telecom cable, or even several meters away. The fiber cable can be existing telecom cable that's been put in place for broadband and datacom transmission, or perhaps put in place simply for the operational purposes by utilities such as yourselves for SCADA purposes, or it can be a special optical cable designed for this particular purpose. The key point is the fiber sensing equipment hardware, or what's called the interrogator unit, is spliced or patched in at a convenient location in a protected area. And a laser signal is pulsed down the fiber rapidly and repeatedly for distances even on the order of 60 miles if desired. So here's the key thing. A small amount of light is reflected back through the fiber length from whence it came, and the reflection is continuously impacted by small amounts of strain that occur in the fiber based upon what's happening in the ambient environment, either right in the right of way or where the cable is placed. So at this point, what have we done? You've now turned a single optical fiber into a continuous microphone of sorts that can pick up all the acoustic vibration occurring in the surroundings along the entire length monitored. It's really pretty amazing. And what do you do with that? You continuously monitor the fiber, and you use the sophisticated software algorithms to differentiate between the normal vibrations you don't care about, the background noise, which has non-threatening activity, and the activity you do care about, the activity that could cause damage to your utility or your infrastructure in general. So perhaps it was activity that was 811 ticketed, so that's all good. Or it can be activity where a ticket was not put in. Or it could be unexpected activity that happens to be occurring right on top of your right-of-way rather than another location where you anticipated it would occur. So some sort of a mapping mistake. For whatever reason, whether it's shovel digging, manholes being opened and entered, construction vehicles, even walking. All that can be identified and classified, and immediate alerts can be provided as desired so that appropriate actions can be taken. Next slide, please. So now that you have that vision, let's wrap up the technology just for now. Some benefits or advantages of this type of sensing technology, distributed fiber optic sensing, include there's one continuous long length of monitoring with no power or electronics along the fiber cable. There's low maintenance and long lifetimes for not just the fiber cable, but the electronics. Typically, fiber cables can last for decades underground unperturbed. Since it's buried optical fiber, it's not affected by electrical impulses or any extreme environments. And then the other thing is, while events can be alerted to camera positioning and drone investigation, whatever actions, there is also no inherent facial recognition. That's very important to many states these days. So it actually preserves privacy. Next slide, please. So think of it as a platform technology with live, real protection, when more capabilities can be built on over time and layered on as desired. So starting at the bottom of this graphic, you have the hardware and you have the fiber layer we already described. Then there's the application layer. Today we're focusing on third-party interference damage prevention, but depending on the utility, there are additional applications that can be provided, such as leak detection for pipes or fault detection for electric grid. Finally, as indicated by the top graphic, there's the data delivery portion that takes place across the application programming interface, or many people know this as the API. An event of interest has been identified, you've classified it, you determine what it is, you've GIS located it, and now there needs to be action. So the action can be a wide variety of things. The action can be multiple and varied depending on what you as a utility owner or a municipality desire. These could include alerting within your established utility control center because you provided data across the API. It could be directing cameras or even drones to fly over and explore what's going on, or sending humans, or it could be simply sending out emails or SMS texts immediately. The key is immediately. It's live protection and you need to do something about it right away. Next slide, please. So while the technology and the software is very sophisticated, it has to be and is designed to be user-friendly at the operator interface. So I'll show you in a slide or so what an energy waterfall looks like, but as in the left screen here, the blue screen you see, but from the customer operator perspective, it can be as simple as a route map where GIS flagged alerts occur, which provide the real-time location and the classification of what's going on. So in addition to automated alerts, by having this in your control center, this provides the human interaction element to decide appropriate action and further investigation. Next slide, please. So I mentioned we're focusing today on distributed acoustic sensing technology, more so than temperature and strain. The reason we're doing that is this lends itself as the most appropriate technology to positively impact and help reduce third-party interference, or what's called TPI in the industry, whether it's unintentional, whether it's intentional, or even malicious. This technology is already being used to protect our nation's borders and perimeters, pipelines, and also provide protection and monitoring for rail and road. So while the hardware is also pretty amazing, I stated one of the big advantages is the software. It's come a long way in the last decade, and the sophisticated programming can now separate normal activities that you don't care about from threats. Next slide, please. So we all know infrastructure in our urban and rural environments experience a great deal of above ground activity. So I'm sure you're asking yourself, how can you separate what's background noise and what you actually care about? That kind of background noise could include vehicles, cars, trucks, trains, making all kinds of noise, farming activities, other machinery, industrial plants. All this noise is actually heard real time by the fiber in the ground, but the intelligence software is used to classify it and locate what we together would identify as threats that are meaningful to your utility infrastructure. such as those listed here. Next slide, please. So this brief webinar, and I do mean brief because we want to go through a lot of use cases, but I'm rushing along here. This brief webinar would not be complete if I did not squeeze in at least one video showing you this actually in action. So we'll hope that it works here. But before we play it, I want to briefly describe what's going on here. Here we have a mechanical digging alert detection example. So you see an excavator in the picture on the bottom left, and it's about to do its thing, which is tap the ground and dump dirt. On the right, you see a scrolling waterfall of acoustic energy. You'll see it scroll in a second here. That's the blue part that's constantly being monitored from the fiber. The software algorithms are constantly looking for predefined threats of multiple categories. Also, the distance along the fiber has been divided into zones. So you can actually turn on and turn off your alerting for a particular zone, depending on what you may know is going on in the area. If you happen to know, for example, that you have 811 activity occurring in an area and you don't want to hear alerts all day, then you turn that off. But basically, you probably want to have most of the time the fiber completely on the entire time. So the system also at this point has been calibrated to ignore normal background noise. The operators are trained, and the standard operating procedures are in place for if and when an alert occurs on the map, you do something about it. The map is in the top left. So now finally, if Erica, you would play the little screen there, you can see the energy as a function of time on the right scrolling. You can see the excavator tapping the ground and digging dirt. And if you look at the top left map, you'll see a map that very shortly will have an alert right along it. And that would be the alert that either sends out messages or sends cameras or alerts an operator. So you see the alert appear. It's as simple as that. From the operator view, they don't need to worry about the scrolling waterfalls and the other things. That's all sophisticated algorithms and software. It's really just what you do with the alert once it happens. Next slide, please. So all in all, we see this technology very synergistic with the mission of Common Ground and you as member companies. So helping to mitigate both the direct and indirect damage costs in the US and abroad. It's very expensive annual damage, which of course results in human life loss too. That's as important or more in the US and elsewhere. So you can't boil the ocean overnight. A great starting point, and hopefully you'll see this through the use cases, would be the identification of high consequence routes where fiber happens to be already located and where perhaps multiple utilities that are in the right of way or close to the right of way might benefit from live protection. Next slide, please. So together, we take first steps and demonstrate, hopefully, how you as members of CGA, including utility owners, municipalities, and others, would benefit from live damage protection and the significant CapEx and OpEx cost reduction that would result through its use. So I want to leave you also with one other thought here, and this is kind of the motherhood and apple pie thought, but it's important to talk about. There's a large potential also for multiple infrastructure applications to our cities and communities. So not only discrete protection of utilities, but also providing additional combined value-added insights. Think of all the fiber that's located underground in the community already. And you've seen the government-sponsored bills that may or may not change as a result of Election Day, but the government-sponsored bills on increasing government and independent funding for infrastructure build-out of telecom and utilities that this country so desperately needs. We have an aging infrastructure and it's inadequate with many of our utilities. So we talk of smart cities and the advantage they'll bring to our future. And the use of distributed fiber optic sensing to protect and monitor our infrastructure will become a big part of that going forward. Next slide, please. And now I'm going to turn it over to my colleagues for a presentation of real-world applications. And with the next slide, John Williams, let's start the use cases.
Thanks, Paul. I'm John Williams. I'm Global Commercial Director for Luna Innovations, Inc., which is an American fiber optic sensing manufacturer. And we have a main brand or product for damage prevention, which is called OptiSense. And I'm very pleased to be with you today. So Paul provided the background on the technology, and then myself and my colleagues from FOSA will provide some real world use cases. We're going to start with power and then move on to different types of utilities. With power cables, there's typically a fiber embedded in the cable or nearby, for example, in the same duct bank. And we can use a dark fiber to provide monitoring. And the main applications are intrusion detection and fault location for where there are power cable faults. Next slide, please. So this example was in downtown Indianapolis, where we monitored around 15 miles of a trunk line in a distribution system. And in an urban environment, these assets were kind of mainly under city streets and, car parks and so forth. So, intrusion was rare. It was mainly at access points like manholes. And we were able to set up zones around those manholes and even set up a detector for somebody lifting up a manhole cover. So that was of interest, both for protecting the buried assets, but also keeping a tag on where maintenance crews are and when and how often the buried assets have been accessed. There was a buried steam line in the same path as the electrical cable that we were monitoring. And that was quite an old piece of infrastructure. So that was causing problems to the electrical cable. So cable faults for the electric power cable were quite common. And, they had historically used electrical pulse generators to find these faults with actually the human ear. So walking out into the field and locating this arcing or where these faults were occurring. So with distributed acoustic sensing, we were able to do that automatically through the detection of the system to pinpoint the location of the fault. So this is very useful when you do have fault conditions, pinpointing the location and then minimizing downtime and making it safer to remediate. So the next slide, please. Pass to my colleague, Alex DeJude.
Hello, I'm Alex DeJude. I am responsible for pipelines in AP Sensing, but also the chairman for the technology committee of FOSA. What I'm trying to show in this slide is that this technology, despite being a recent technology, is widely used in many different fields. In this case, I'm showing a summary of multiple power cable projects that we have, quite a few in United States, Florida, California, etc. And also in France, Italy interconnector. You see this picture on the right showing Torino to France. Torino is a very busy city where Fiat is made and so on, very industrial town. And so these cables pass through very urban areas, and we've done many tests there. Also on the picture shows a service tunnel there in New York, where the power cables are monitored there. So in total, we have several applications, more than 150 miles, and the applications include the TPI protection. So these cables were tested in many places with real diggers and all sorts of activities, like jackhammers and drilling machines in different areas. Rural area may seem quiet, but it's not. You have very busy agricultural activities. and very noisy, and they impact the soil very close to the cables. So we have to be reliably detecting and avoiding false alarms. So you need to classify those activities very well. Next slide. For pipelines, is a similar activity. So we are monitoring the right of way, sometimes with more than one pipeline there, with monitoring using telecom cables that are used for telemetry of the pipelines. These are cables that are buried inside conduits parallel to pipelines. TPI, third-party interference, is often the main driver for the monitoring of the right-of-way, but also we provide other activities like leak detection, for instance. And this is done for water, big trunk lines, and gas and hazard liquids. Next slide, please. What I'm showing here is again, try to make the point that this technology is widely used, being extensively tested by Epicensing and the other vendors here. We have 453 miles of pipelines and more than 500 tests that we've done, TPI tests being performed on those pipelines. Here on the right, on this picture, show like a montage of collage of different machineries that have been used for tests, big diggers, small diggers. Even on the bottom left, you know, a small guy and a big guy doing manual digging, all sorts of construction activities, including explosions and other things. On the bottom right, what you see is two tests done simultaneously on a 40-kilometer monitor cable, and you see on this vertical bright blue lines. These are normal activities along this pipeline. It may be agricultural activities, it may be road crossings, it may be that the pipeline is passing parallel to the pipeline. So you have the pipeline is passing parallel to roads. So there normally a pipeline will have many of hundreds of road crossings and urban areas and all sorts of activities. And in different soil types and environment conditions like dry and very wet, etc. Next slide, please. I'll pass to my colleague here.
Thanks, Alex. Good morning or good afternoon, everyone. My name is Stephen Coles. I'm with a fiber optic sensing company called Hi-Fi. At Hi-Fi, we're actually partly owned by Enbridge and a very large midstream operator in Canada called Synovus. So as a result, our entire focus is on monitoring pipeline infrastructure, and we use a slightly different version of the technology that's designed specifically for detecting really tough pipeline conditions like pinhole leaks in low pressure type conditions. The application case study here, or the illustration that we're showing, very similar to what was just presented previously from the perspective of ground disturbance monitoring. But what's unique about this one situation is that while we have this 150-kilometer pipeline that's liquids based, we actually have multiple deployments of fiber sensors along a specific section of the pipeline. So specifically, we have a fiber sensor that's on the pipe. Externally, we have a fiber sensor that's off the pipe, about 3.5 feet away from the pipe. And we also have a fiber optic sensor that's inside the pipe, or what we call internal deployment. These latter two are very, very important from the perspective of the potential of retrofitting existing pipes with distributed fiber optic sensing technology. And you can see here, we did a variety of tests from a ground disturbance monitoring perspective, all of which were detected independently by each of the different sensors very effectively with very high signal to noise ratio, with both high definition acoustics and strain that can be pushed to the control room of the operator in this case, with detailed information, even directionality of the travel of the machine as an example, and even high definition acoustical wave file that can be received seconds after the event has been detected. And we detect it not just because the event is loud, but we're actually focusing in with algorithms on frequencies and harmonics that are unique to machinery. And as a result, this becomes much more preventative in nature rather than just reactive. And in addition, we can do a variety of other applications that can be supported, obviously, things like leak detection, geotechnical monitoring like earthquakes, thermal anomalies, operational activities such as pig detection, analysis, and distributed flow monitoring can also be provided. I'll hand off now to my colleague, Doug from Optic.
Doug, you're on mute if you're speaking.
Okay, apologies for that. My name is Doug Gibson. I was the original founder of the company called Optic Solutions. It was sold to British Petroleum a couple of years ago. And as you can imagine, at BP, what we're mainly interested in is ensuring that there's zero emissions, zero failure of the pipeline infrastructure. And of course, what we see nowadays, as you saw from the other presenters, is that most of the threats to pipelines is external. You know, BP and other companies design their pipelines not to leak. And so unless it's very aging infrastructure, we see very, very few leaks on pipes that are internally itself. A lot of what we see is attacks on the pipelines. We see digging, as you saw in the other examples. And you can also imagine that for lines such as processed product, there's a lot of attempts at theft. This particular example was a pipeline in India where we saw 26 theft attempts in 6 months on this pipeline. This was a line that was taking a petroleum product and therefore it was very valuable. And in this particular case, it was very strange because we saw the pipeline activity, we saw the digging activity, but when the security companies went out there, there was nothing there. There was nobody there. And of course, that inevitably led to the discussion, oh, well, you've got false alarms, the problems with the system. But what we actually found was that someone had dug a tunnel up to the pipeline and was attaching a spigot on the pipeline and to try and take product away to a bungalow that was about 100 meters away from the pipeline. So here, not only were we able to find the digging activity, but we were able to stop the threat of theft, but also catastrophic damage. You can imagine a highly combustible product going through the pipeline. And these guys don't take care. They don't. It's a very haphazard approach to stealing product, and a lot of times ends up in death and destruction around the pipeline. So we were able to alarm on the attempt of theft. The security team were alerted. The thieves were apprehended, and importantly that we were able to compile the evidence around the theft based upon the data that was taken. So this technology, as you've seen from several presenters, is hugely valuable to pipeline companies, and I hope you see the value in it. I'll pass on now to OptiSense.
Thanks, Doug. Yes, in this example, this was a gas utility in North America. So, you know, gas utilities, are up there with telecom in terms of damage costs in North America and frequency of damage. And there's a huge focus on, when you deploy this technology, providing accurate data into wider integrated response mechanisms. For example, integrating it with the one call ticketing system, and the data you produce has to be accurate. And Doug mentioned false alarms and so forth. So we have done a number of tests, as have the other vendors. This is just an example of site acceptance tests that we do for most projects, where different types of intrusion tools are tested in the field, and that can produce an acceptance of the system into operation. So this example, we performed with 100% score, and there were 5 false alarms per month, which was deemed acceptable by the operator. And all of our systems are provided with a support package to continue to help operators get the best value from these kind of systems. Next slide. So also clearly telecom assets are ubiquitous and very important to protect, and have the fiber, typically a dark fiber or a different wavelength available. And there's intrusion as a key driver, but there's also a cybersecurity from kind of physical security standpoint concern, that people are accessing fiber closets or other access points along the network that these kind of systems can monitor for. The right-of-way, particularly high consequence corridors, are going to have often multiple different utilities, and even if the fiber is several feet away from these other assets, that fiber can be used to protect the whole right-of-way. So that's a key driver for us in our mission to help with reducing damage prevention, is to leverage those dark fibers in shared right-of-ways. Next slide, please. In this example, this was out in California. This was a high traffic cable to the Silicon Valley area, and this was a big problem because there was a cable cut on a high traffic line, and a lot of the tech companies were extremely unhappy with the outage, and I think there was even a company doing their quarterly earnings report that got impacted by this. And we were kind of deployed after the fact to not have this kind of issue again. The system testing was very rigorous, and we did testing of access points, and near the railway, you can see this line here. That's actually a train passing. So they wanted to know that the fiber wasn't being impacted by the railway, and we were part of a damage prevention approach for that critical line going forward. Next slide.
I was caught trying to answer a question, but I am pleased to say that we are Q&A. So I'm gonna wrap it up in the next 2 slides. Thank you for everyone for your not only your attention, but for the panelists here for basically going through a wide variety of use cases in addition to the technology. To summarize, I hope we've shown you that distributed fiber optic sensing is proven technology. It's been around for a long time. It's always improving from a software algorithm perspective, and it's already being used for third-party interference along with other purposes. We see the applications for damage prevention opportunities quite clearly. It's just a matter of, I think, having additional dialogue with knowledgeable folks like yourself. So the live right-of-way monitoring of underground, single, or preferably, as JJ just said, multi-use assets could be a significant adder to minimize damage and enhance life safety going forward, along with everything else that Common Ground Alliance is so valiantly doing. It could be a powerful addition to existing efforts to drive, hopefully, faster and closer to zero damage, which is everyone's mission here. And the utility and telecom providing members would realize in the process significant additional cost savings in live damage prevention on these damage prone routes. So I just realized my video is not on, so I will turn it on. The challenges are starting out and prioritizing routes and coordinating and funding how to make this work in a concerted manner. We're going to get to that in the final slide in just a second, but I do want to mention this also as the plug for the Fiber Optic Sensing Association. We just like Common Ground Alliance, welcome new members. We welcome new members. So if you're interested in becoming a member of Fiber Optic Sensing, please contact myself. And even if you're not, we're interested very much so in engaging with you on everything we talked about today to try to identify best locations and best advantages for you as a Common Ground Alliance member company for win-win advantage. And then the final slide, please. So possible next steps that we've talked about with the Common Ground Alliance Technology Committee and several member companies is to simply use this as a stepping stone to increase the collaboration opportunity between our organizations. We want to get together, perhaps our technology committee, folks on your end, and answer questions like the following. I'm not going to read those questions to you, but there's a wide variety of things that we need to learn, since we are not the experts you are in the types of damage that occurs, and you're not the experts we are in how to implement the technology. We want to understand how best to implement it, what the limitations are, what the advantages are, what the cost benefit analysis can be. And frankly, I mean, when it all comes down to the bottom line, how can we together help you and us drive on the road to zero? How can distributed fiber optic sensing drive efforts toward zero damage? So I'll let you look at these questions throughout the Q&A. And maybe with that, I'll turn it over to our esteemed staff here at Common Ground to start off the Q&A in the time remaining. And we should have as much as 15 minutes if we need it. Thank you so much for paying attention and for your upcoming participation.
Well, Paul, certainly appreciate your leading this effort, but thanks to you, to Alex, to JJ, to Stephen, and to Doug for a very thorough, comprehensive, exciting, fantastic presentation on some incredible technology that's being used now. As you pointed out, you gave some great illustrations of this is not future, this is now. And what can we do? How can we help promote the use of that technology to help us with our goal of reducing damages? We're going to throw it open now for your questions. Matt Briggs is going to help me with fielding the questions. And again, a reminder for you, your tools, both the chat and the Q&A tool are available for you to field questions to us. We've received a couple of questions already. So with that, Matt, if you're ready, I'm going to let you jump in.
And thanks again to the team for the presentation today. I think it was fantastic, and hopefully it allows a lot of people that are listening in today to really kind of think about this technology and think of ways this can be applied in the space. So thanks again to everybody. We did have a couple questions, as Steve had mentioned. The first one, fascinating technology. What are type 1 and type 2 error rates?
Did anyone recall that comment? Because I don't. So somebody on the panel must.
Yeah, I'm not sure, Steve, with Hi-Fi, I'm not sure it was referenced in the presentation per se, but this is the mapping of true positives and false positives, effectively around type 1 and type 2. I think there was some commentary about, the technology is not impervious to having some false positives. The low levels have been deemed sort of acceptable in the one example that JJ mentioned at OptiSense with the client. We've all done all kinds of different testing, whether it be on pipelines for things like leak detection and ground disturbance monitoring, where we've all scored very, very well in terms of hitting very high, if not 100% performance on true positives without false positive alarms impacting the accuracy. So I don't know if that's directly answering your question. We don't have those direct data to be able to provide, but directionality from a directional perspective, I mean, the performance has been fantastic from a type 1 and type 2 perspective.
Yeah, I think you covered it well, Steve. I would just add that there is a way to further reduce, false positives or nuisance alarms through the logic and integration of how that data goes up into different platforms. For example, if you have one call system, you can see where there's permitted work and where there's unpermitted work, and assign a higher level of threat to unpermitted work, for example, and that would further reduce those kind of errors. That's an example.
Great. Thank you, folks. Another question that had come in, can you talk about the material or installation constraints for fiber locations to ensure the technology works well?
Sure, I'll start that one off, and then maybe others can chime in if you can hear me. Let me see. Do I have my? Yeah, you can. Okay. So the technology, as you might imagine, is extremely sensitive, and thus it's forgiving in many material and installation configurations. So that's why we keep talking about it doesn't have to be right in the right of way. It doesn't have to be even a few feet away. It could be meters away or multiple meters away, and still pick up that some damage is about to occur that gets classified. Now, in terms of material installation configurations, the first thing I'll say is that, there are many different types of installations depending on the industry that vary in depth, that vary in whether it's in a particular type of cable, how the cable's constructed, whether the fiber is encased in concrete or behind barriers. It all comes down to how well acoustically coupled for this particular application the fiber is going to experience the environment. And we have actually guidelines established within the Fiber Optic Sensing Association through our technology committee and the great work that they do to help provide that guidance. So the short answer is that it's going to work well in almost every situation for third-party interference. When it comes to more demanding applications like detecting millimeter-size leaks in gas lines and others, then maybe you have to be a little bit more constrained in location. But we have the ability, if anyone's interested going forward, to work with you and talk about how your fiber is laid out now, how it's constructed, and the probability of it working well in that particular location. And then for greenfield, that's the most exciting part, because as this technology is further adopted, we will be able to help entities who want to put in new fiber, put in the proper fiber in the proper location to take advantage of this technology. Anybody else want to add to that?
Yeah, Paul, Doug here. I think one thing about the installation of fiber, a lot of the times we have to rely on fiber that's already in the ground. So we don't always have the ability to put in new fiber with a new pipeline. So a lot of the times we use fiber that's been put in the ground by telecommunication companies, which are typically several meters away from the pipeline itself, but still within the right of way. So we have to be able to sense from those kind of communications fiber rather than always have a new fiber available that's been put in there with the pipeline. So we're not constrained to pipelines that have fiber on the pipeline itself. It's always better to have that, but as I say, we typically have to deal with fiber that's a few meters away from the pipeline and installed for other purposes.
And then in terms of equipment locations, you're talking about, you know, within every 50 to 100 miles, you'll need an equipment location. And in the rack cabinet, you know, it's pretty low power, a couple of hundred watts, a few hundred watts, and a few U of rack space, 4 or 5 U typically, for the equipment installation. So that's a constraint there, just on the equipment.
Perfect. Perfect. All right. Chat from Robert. Can you folks please expand on how it will be recognized and identify 2 events and alerts happening simultaneously?
Who wants to take that one?
It's really about the threat profile of along the asset, of how the systems are configured. So, and then the algorithms focusing on what the operator has designated in their threat profile as a threat. For example, backhoes or other construction tools are designated as threats, and you will, you know, focus on the signatures of those types of activities. For example, the tonals or the impacts of a backhoe. You know, there's a number of different things that go into the classification of those in terms of the signal, and you discriminate that from other activity. And you can also, you know, localize these systems so that they're focusing on the right of way rather than activity that's from further away, outside of the right of way. You know, that's a technique that is used during tuning and calibration of these systems, because you can get a very loud noise far away and something, you know, less noisy closer that you're more interested in. So that's a key part of that process. You do need to be very prescriptive in your threat profile approach.
Yeah, just to add that on the slide that we showed an example where you had 2 diggers digging simultaneously over a 40-kilometer pipeline, and this was done exactly to show the principle. The fiber is divided in zones more or less 5 meters, for instance, and you can have as many events as is possible, right? So not going to be a problem to have 100 simultaneous events if you are in a war zone, for instance, right?
Yeah, the way the fiber operates is that we can zone the fiber, and typically each of these systems will all have an accuracy of anywhere between 1 and 10 meters. That means that we can distinguish separate events within those zones. And so we can see a digger at one point and perhaps a digger 50 meters away at another point. And they will act as 2 different alarms and send the operator alarms for each individual event. So we can distinguish along the fiber different events happening at the same time.
Perfect.
Great questions. Let's keep it going here. We have 5 more minutes, right? Or thereabouts.
We probably have time for one more, and then we'll want to go into closing here. So I do have one more. It's actually a use case specific in terms of the hi-fi use case. I think that's with Stephen Coles. Can this be deployed only for new pipeline builds, or can retroughing of existing pipelines be supported as well?
Yeah, great question. In fact, that was one of the points I tried to make on that slide, is that it's, there are 2.5 million miles of pipeline, as an example, in the US alone. Just deploying this on new pipes, while it's easier when the pipe is being deployed in the trench, of course, to have the fiber or conduit placed with the pipe, we're getting a lot of interest in retrofitting existing pipeline assets, particularly as they're being looked at to being repurposed to carry other product types like CO2 and even hydrogen. So we actually have been quite involved in retrofitting existing pipelines. We do that either externally by placing conduits upwards around 3 or 4 feet away from the existing pipe, and there's new technologies and vibratory plows to be able to do that. Or we can go inside the pipe, and that was that internal deployment that I referenced there. Really good for short, high consequence areas. I apologize, I'm from Canada, so I speak metric, but sort of upwards around 4,000 or 5,000 meters or so, where you'll actually have the fiber optic sensor in a stainless steel capillary tube, and we can literally pull and push that line into place for river crossing or an environmental zone that is short in nature, but also very high consequence in nature. So yeah, a lot of interest these days in retrofitting existing pipe assets.
Fantastic. Thank you, Stephen. All right, I know we have a couple minutes left, so I think from a question standpoint, we should be good to go. If there's any other questions, feel free to email the guys here. I will toss it over to Steve Light here in a second, but just from my standpoint, again, thank you to the FOSA members for your presentation today. I think what I'm really excited about in this webinar series is just having the ability to have experts like yourselves in your respective fields, and being able to showcase these technologies and just kind of continue to develop this thought around the CGA community on these topics. So you guys started us off with a bang. It's much appreciated. And with that, I will toss it over to Steve Light for closing.
Thank you.
Well, thank you, Matt. Thanks again to our panelists for an outstanding presentation. Special thanks to Nick Starkey and Matt Briggs for helping put this whole thing together. So we appreciate their support. Those two gentlemen are members of our technology committee, as we pointed out before, and its involvement in the list of committees that you see here on your screen, that involvement helps CGA continue our drive forward toward reducing damages. So I encourage you to take a moment to look at this list and see the committees, and let us know if there's a committee that you think you would like to serve on. We can always use more good folks to help us with that drive towards reducing damages. If you're interested in learning more about any of the committees, you can certainly email the email address that's listed there, support@commongroundalliance.com. Also, I'll have a slide up in just a moment to give you an idea of how you can get in touch with some of the CGA staff directly as well. But before we go, did want to mention you should have received emails already announcing that we are taking registration now for our 2023 CGA Conference and Expo. It'll be back on the East Coast in Orlando, Florida this year, April 17th through 21st. There is a very diverse agenda that is in the process of being scheduled, but that agenda is also going to include interactive exhibits, including for the first time, I believe, outdoor exhibit area that we're calling Dig, Demo, Discuss. And there are also going to be some special tours that are going to be provided for folks who are interested in the Florida area that are actually going to be work related, but give you a chance to have a little bit of fun too. So certainly encourage you to check out cgaconference.com for more information on the agenda, and to go ahead and sign up and register. We hope you'll be there. We had over 800 folks at our conference in 2022, and I have a feeling we can kick that total a little bit higher as we come back to the East Coast to Orlando. And then I believe the last slide gives you just more ways to reach out to any of us. If you want to specifically reach out to Nick or Matt or any of us related to technology committee or report questions, the email there at the bottom, technology@commongroundalliance.com. Our technology hub was rolled out back during the summer. Technology.commongroundalliance.com is the address for that. There you can see the case studies in the technology report, and that's where this particular webinar video will be hosted. And then finally, reach out to Erica, Sarah Magruder-Lyle, or me if you have questions about anything CGA related, and especially if you'd like to learn more about the technology committee or any of the other committees. Don't hesitate to reach out. We're happy to help. So with that, I believe we are wrapping things up. Thanks again so much to everyone for their involvement, and those of you who gave us your time. We hope that this was of great value to you, and we look forward to wishing everyone a good, safe day, and wrapping up the year in a safe manner as well. Take care, everyone.
Thank you.
Thank you. Take care.
Thank you.
Thank